I'm Michael Previte. I'm the co-founder, CTO, and SVP of R&D at Element Biosciences. The way that we built this chemistry was really to make the sequencing part as minimal in terms of introducing error into the read as you could possibly get. And that's kind of why we stand at the higher end of the field today, or at the top of the field with quality, is because of the fact that we do things very differently than people have done in the past. Really, once you've done your library prep and transformed the DNA, you have to capture that DNA on your surface in some way. And that's a single molecule of the full entire library. That single molecule, if you were to try to read the bases from it, you need highly sophisticated detection modalities for you to be able to see it, because it's only a single molecule. So what people typically do is they'll amplify that single molecule. And the amplification techniques vary. The original ones were PCR-based amplification techniques, where they'd called bridge amplification. That was really introduced by Illumina, but I think it was probably George Church that was the first one to really investigate and use that. And that technique is much like PCR. So it would introduce an error that would propagate through the amplification. And then ultimately, that's going to be on your readout from your sequencer if there's an error that's introduced into that amplification step. For Element, we use a circle amplification, where we capture a ligated circle. We amplify that up with a polymerase. And that doesn't have the perpetual propagation of the error like you get in PCR. If an error happens, it happens randomly in the stream, and essentially it doesn't propagate throughout all of the amplified DNA that you're looking at. And so that's two different kinds of error that's introduced by amplification. Once you've amplified those libraries, then you have to read the sequence out. And reading the sequence out really is going to be dependent on the polymerases that you're using to read or detect the base of interest. And in base classification, that polymerase is introducing a labeled nucleotide. And that labeled nucleotide in the cases for Element or Illumina or can be introduced in different ways. So typically, the methods of the past were used to introduce incorporation through a labeled base that gets incorporated. And that incorporated base with the polymerase, it's only incorporated correctly if the polymerase gets the correct base and puts it in. For Element, we use what we call avidity chemistry, and that's basically a chemistry where the avidity molecule binds and essentially is coerced in multiple spots on the same strand. And so you get a combination of multivalency that allows you to get the readout of the technology in a way that's not done on any other platforms. Both of those reading techniques introduce different kinds of error. And the kinds of error that can come through that, maybe through phasing and pre-phasing, such that the signal deteriorates, have a harder time picking up what the base classification is. And so the quality of your reads starts to deteriorate as you start to get more and more mixtures of colors. Whereas in avidity chemistry, that mixture of color is prolonged because of the fact that you have to bind multiple sites, and those multiple sites prevent a lot of that phasing and pre-phasing mixture. And that's just, Element and Illumina and BGI and some of these complete genomics when they came out. Some of the other techniques like PacBio and ONT have more random errors that are associated because of the fact that it's sort of an asynchronous sequencing process. And each of those has, different values and deleterious things that are associated with those kinds of sequencing techniques. Phasing and pre-phasing and synchronous sequencing systems is, a very important quality or metric that's tracked. Phasing is really a result of when strands in a group of strands fall behind. And essentially, if you have 100 strands and one of them isn't completed, so they all put a G in except one, and then on the next base, that base is a C and that G is still hanging there, that's going to introduce a false color. Pre-phasing is when you have that same group of strands and one actually reads forward or skips a step ahead while the other one stays synchronized. So that also introduces a false color. And so what happens in traditional synchronized sequencing is strands get out of phase, where they start to become unsynchronized. And as a result of that, you start to introduce false color into your sequencing. chemistry. So if I have 100 strands, as I start to go along in my sequencing cycles, I will start to build up more and more false color in the wake of the right color. As a result, you start to deteriorate the quality of your signal over the longer reads, and people notice this with their sequencing systems. As you get out to 150 or even some of the systems that go to 300 base pairs, you start to see this deterioration in quality and a drop-off. And that's really in part due to this phasing, pre-phasing term. For Avidity chemistry, we have created a multivalent system, which ironically, when we started the company, we always said, well, signal noise matters, and let's get the background down for the surface chemistry. And one of the people here said, well, nobody cares about that. They just care about phasing. If you can't fix phasing, pre-phasing, then you're always going to be battling against the false color that's building up in what you're trying to read. Well, Avidity chemistry, surprisingly, serendipitously, helped solve that problem. Because of the fact that the Avidity molecule, if you had 5 of the nucleotides come in and bind simultaneously, if one strand is phased, well, you miss that one strand, but you still have the same color because the other 4 are the most predominant ones that are bound. And the color is based off of that Avidity complex. If 2 strands become phased, I still have 3 that are bound. So in reality, phased or pre-phased, in reality, what we're creating is we're creating sort of a way to mask phasing and pre-phasing, which really has allowed us to evolve the chemistry very rapidly, as you've seen with some of the cloud break technology that we've put out and some of the promise for the 2x300 technologies that we'll be able to put together. So it's been serendipitous that we came across or thought about Avidity chemistry, and it's also had some advantages in some of the areas that we were challenged initially by saying, well, signal to background is not the only thing that matters.